Welcome to Chem Vid. Today we're talking about Hess's law, and Hess's law relates to enthalpy. Now if you recall, enthalpy is a state function, meaning it can be calculated in multiple ways. In our first set of notes, we learned about using Q equals mc delta T to find the heat and then dividing by moles. That was one way. Another way was using enthalpy as a conversion factor in order to find out how much heat was released. Today we're going to use a system of equations. But before that, let's have a quick review. Alright, number 1. Label the following as endothermic or exothermic. As we talked about before, exothermic means heat is exiting the system. That's why it starts out with EX, or so I like to say. Endothermic means heat is being absorbed into the system. EN, enter. Okay? So it's very important to have those straight. A positive delta H means that I am absorbing heat. It's what we use for endothermic. A negative delta H means that heat is being released. So a negative is exothermic, a positive is endothermic. So when I look at this guy, melting ice. Melting ice is going from a solid to a liquid. So solids are very structured, and liquids are more free-flowing. We know that. So I need to look at who has more energy, because enthalpy is all about energy. And if I look, solids have a lower energy than liquids, because liquids have more energy because they can move around, whereas solids are very structured and they don't move around as much. So looking at this, if I want to get a solid to a liquid, do I have to give a solid energy, or do I have to take energy away from a solid? The correct answer is give. I need to make sure that if I give energy in the form of heat, then those molecules can actually absorb that energy and start moving around faster to become a liquid. So in this case, melting ice is an endothermic process, or a positive delta H. Now what I want you to do is I want you to pause the video, and I want you to try to label the rest of these as exothermic and endothermic. Think about what's happening and label them accordingly. Alright, so hopefully you gave that a shot. Hand warmers release heat. You can feel that they get warm. So therefore they are exothermic. Combustion is when you have something that's on fire. That's definitely releasing heat, so I'm going to say that is exothermic. Freezing ice is going from a liquid to a solid, which means I'm going from more energy to less energy, so I am going to have to get rid of some of the energy, making this exothermic. This makes sense because if one way is endothermic, the other way has to be exothermic. So in phase changes, whenever you go forward or backwards, they're always opposite. One is gaining, one is losing. Boiling water. Now boiling water, when I have the heat, it feels hot. But you have to think about what's happening at the molecular level. A liquid is turning into a gas. So we have energy into a whole lot of energy, right? Which means that my liquid has to absorb energy to turn into a gas. So boiling water is actually endothermic because the liquid has to absorb heat to turn into a gas. It feels hot because we're feeling the heat from the stove. Alright, cold packs. Cold packs absorb heat from your body, which is why they feel cold. And so therefore these guys are endothermic. Now let's do photosynthesis. Photosynthesis is when you have a plant and they're in the sun and then they make food. Well, a plant is in the sun and it has to absorb the sun's rays in order to create food. So in this case, photosynthesis is an endothermic reaction. The plant is absorbing energy from the sun in order to create food. Okay, so Hess's law, let's get started. Hess's law has 3 specific rules. We're going to go over these rules and then use number 2 as our example of using these rules. Okay, so Hess's law, it states that the sum of the energy or the enthalpy changes for individual reactions is the same change that happens for the final reaction. In other words, energy is conserved in a reaction. So I can use multiple reactions to find the energy absorbed or released in another reaction. So here are my 3 rules. If you switch the reactants and products, you need to switch the sign. If you multiply the coefficients, you need to multiply the sign, multiply the delta H. And if you add together and cancel the terms that are common on both sides, you will find the delta H of the new reaction. So right now, just copy those down, and then we are going to use them. So pause the video, copy those down, and then we'll go on to our example. Okay, so in this question, I want to know what the enthalpy change is for this reaction right here. But I only have these 2 reactions and their enthalpies. So what Hess's law says is that I can rearrange these reactions to form this reaction, and once I rearrange it, I can calculate the delta H of this reaction. So first what I want to do is I want to start off, and I want C2H4 as a gas as a reactant. So I look at my possible equations, and I notice that the first equation has C2H4 as a gas as a reactant. So I am going to write that out. Now, because I didn't actually change anything in my equation from up here, I'm not going to change the delta H. The next thing I want to look for is the H2O as a liquid. And it needs to be on the reactant side. So I look up here and I see that, oh, this one has H2O and this one has H2O. Now I've already used this first equation in order to have the C2H4. So I'm not going to use that equation again. I'm going to use the second one. And I notice that H2O needs to be a reactant, and over here it's a product. So just like in math class, I am going to flip the second equation so that my reactants and products are on the correct side. So I start writing this guy out, only I'm going to flip it. Now because I flipped this equation, so now my reactants are products and my products are reactants, I need to follow Hess's law, which says that if you switch the reactants and the products, you have to switch the sign of delta H. That means that this reaction going forward, my original reaction was exothermic. But if I do the same reaction backwards, it's going to have to be endothermic. So I'm going to change that sign to a plus. Now I am going to look, and the last thing I need is C2H5OH as a product. So I look and, oh, look at that. It's already a product over here. So I've already taken care of that. So that means that I have used my equations correctly, and I have my C2H4 as a reactant, water as a reactant, and C2H5OH as a product. I'm good. Now I just need to follow the last part of Hess's law. Add together and cancel terms that are common on both sides. So if I look, there's 3 O2s right there, and there are 3 O2s on the other side. So since I have O2 and O2 on the reactants and the products, I can cancel those out, just like in math class. I have 2 CO2s and 2 CO2s that are on opposite sides. And then I have 2 waters over here and 3 waters over here, so I am going to just cancel out 2 of them. and there's 1 water left over. Now that I have canceled out all of the stuff that is extra, I am going to add these terms together, like so. So the C2H4 comes down. There's 1 water left over, so that comes down. And then there is 1 C2H5OH that comes down. So I added what was remaining from my 2 equations, and I created a new equation. And if you look, this equation matches the equation that I wanted to create. So that means I did it right. I used my equations correctly. Then, in order to find the delta H for this new reaction, I'm going to do the same thing. I'm going to add my enthalpies together. So I'm going to add a negative 1,000 plus a positive 1,000, and I get negative 43.6 kilojoules of energy. So up here, use the values and Hess's law to determine the enthalpy change for this reaction. The enthalpy change for this reaction is negative 43.6 kilojoules. And I calculated that by using a system of equations of other reactions and their enthalpy in order to solve for the new enthalpy of a new equation. So here I have it written out a little nicer, but it's the same thing. You're going to flip in order to make the products and reactants match. You add up the energy for the total reaction for your new equation. And by looking at the sign of delta H, I can tell if it is exothermic or endothermic. In this case, because there is a negative, I know that this reaction is exothermic. So let's try another one. Number 3. These are the reactions I am given with their enthalpies. This is the reaction that I want. And so I am going to try to rearrange these top equations right here so that they match this equation right there. Alright, so I know that I want P4 as a reactant. This first equation has P4 as a reactant, so I'm just going to write it down. P4 plus 10 Cl2s go to 4 PCl5s. And because I didn't do anything, I'm just going to copy down the enthalpy that was originally with it. Then I look over here and I see Cl2, and I see that Cl2s are on both sides. I already have it, so I'm not going to worry about it. Then I see that I want PCl3 on the product side. And if I look up here, PCl3 is on the reactant side. So I am going to flip this equation, and I am going to rewrite it flipped. So now I have them flipped, and I changed the sign of my delta H because now the reaction is endothermic instead of exo. If I look up here, it says that I want 4 PCl3s, and in my equation I only have 1. So I'm going to go through and I'm going to multiply my equation by 4 so that I have the desired amount of PCl3s. And according to Hess's law, my second rule, if I multiply the coefficients, I have to multiply the delta H, because now more energy is going to be released because there is more of it. So I'm going to multiply that by 4. Next, I'm going to cancel out anything that is the same. So let's see, P4 stays the same. I have 10 chlorines on this side and 4 chlorines on this side. So all of these chlorines cancel out, and 6 chlorines remain up here. 4 PCl5s on this side, 4 PCl5s on that side. So when I rewrite the equation, I have a P4 plus 6 Cl2s go to 4 PCl3s. Done. I added those together and it worked out beautifully because it's the same as the equation that I wanted. So I add the delta H's to get my answer. Because the sign is negative, it's exothermic. Here's it written out a little nicer. And for your homework, please do 4, 5, and 6.